ลิสาเอ็มสวัสดิกุล
People have been measuring things for 1,000 years. We measure time, temperatures, mass, volume, and many more.
As we can see, measurement plays a big part in people's daily lives. In the past, people used hands, arms, and fingers to measure things. But how can we know that our measurements are the same?
It would be so unfair if we're going to use our arms or hands to measure it. Therefore, we need a standard system. That is why the scientists developed the system. It's called International System or SI units. Now, everyone uses the same language of measurement. For example, everyone knows that 1 inch and 1 inch is the same for everyone.
Moreover, with prefix for multiples and submultiples of SI units, make it easier for us to convert between units with some mental maths. Let's say if I want to travel from Bangkok to Chiang Mai, I would not say I travel in units of meters. Why is that? Because it would be about 564,760 meters. Wouldn't it be easier if I say it is about 564.76 kilometers?
Yes, but if we want to talk about something as well as the mass of a atom, we would say a mass of oxygen is about 19.94 kilograms, or 19.94 to the power of negative 24. Here is the table of the prefix. This table contains 20 kinds of prefix, which 10 of these is the positive power prefix, and another 10 is the negative power.
Let's get on to the fundamental units of or the basic units of SI. The basic units are meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, candela for luminous intensity, and mole for amount of substance. Where do they come from? Here are some examples. Second defines as in 9,192,631,770 oscillations of cesium-133 atoms. Meter defines as distance that light traveled in 1 over 299,792,458 meters per second. And kilogram comes from mass of international prototype.
Interestingly, with these 7 basic units, we can derive as many more we want, which are called derived units. This table shows some of derived units. Let's see some examples. Electric capacitance or farad is formed C divided by V. C is electric charge in coulomb. Coulomb is formed ampere second. V is electric potential in volt. Volt is from kilogram meter square per ampere second square. Therefore, farad is ampere square second to the power of 4 per kilogram meter square. Other derived units are such as Joule for energy, Newton for force, Pascal for pressures, and radians for plane angle. How do the scientists get these units? Let me introduce you some of them. Coulomb is the quantity of electricity flow in 1 second by a current 1 ampere. Pascal is the pressure or state equal to 1 neutron per square meter. Neutron is the force of mass 1 kilogram with an acceleration 1 meter per second square.
As we are in the field of electrical engineering, let me show you some of the commonly used units. I am going to put in voltage into the circuit so that LED will light up. Voltage is one of the fundamental units for electricity. It is a measure of electrical energy of how much energy is pushing the electron in the circuit. Something else also happens in the circuit. There is a current flowing in here. Current is measured in terms of ampere. Voltage allows current or electron to flow. And here is the real connection. And as mentioned before, current will flow from negative terminal through the circuit and into the positive terminals. Here I will put in resistor in the circuit as well. Resistance is one of the three fundamental units. Resistance opposes the flow of current. Other units are farad, coulombs, as mentioned before, Siemens for conductance, joules for energy, watt for power, Henry for inductance, hertz for frequency.
Now, allow us to show you the fundamental of electricity, magnetism, and circuits. As we already know that the flow of current is the flow of electrons. But if we take a step deeper, we will know that there are two types of flows. To make it easier to see, I will show you a simple picture to illustrate. This is a simple circuit with a light bulb and a battery. A battery consists of two terminals. The shorter one is the negative terminal, and the longer one is the positive terminal. The current will flow from the positive terminal through the wire into the light bulb. The bulb will light up, then the current enters the negative terminal. This is called conventional current. This is the idea formed by the 7th century scientists. Now that we do really know is that the current is actually flowing from the negative terminal to the positive terminal. This is called the electron flow. Let's move on energy in an inductor. Inductor is a coil that stores energy in a magnetic field. When it has only a small energy, it will generate a magnetic field and resist sudden change in current. If we lower the amount of current flowing through the system, the stored energy will fall as well. When we increase the amount of current, the coil or the inductor will absorb energy. On the other hand, if the current falls, energy is released. Now I will show you the equation of the energy in an inductor, which is W equal to 1 over 2 Li squared, where W is the energy stored in the coil in Joule, L is the inductance of the coil in Henry, and I is the current in ampere.
To make it easier for you to follow, I will show you a video about the experiment showing how energy is stored in a capacitor. Starting with a battery, a switch and an LED. When the switch is pressed, the LED will light up and slowly fade off. Now he is going to show us how the capacitor stores energy in the device. When the switch is pressed, light will bright up as seen. The switch he is pressing now charges the capacitor. Another switch is pressed to show the stored energy in the capacitor.
Here are the common impedance of AC circuit. The first two diagrams are inductor and capacitor relatively. The equation for inductor is 2 pi fL, and for capacitor it is 1 over 2 pi fc, where f is the frequency. The next two is the series connection of resistor inductor and resistor capacitor. Dash impedance is the sum of the square of the two variables, then take the square root of the whole equation. The fifth diagram shows the series connection of resistor, capacitor, and inductor. The equation of its impedance is shown here. Then, next two are the diagrams showing parallel connection between resistor inductor and resistor conductor. To find the impedance, we multiplied the two variables together and divided by the square root of the sum square of the variable. The last one shows the parallel connection of capacitor with the series connection of resistor and inductor. And here is the impedance equation.
Let's move on to some fundamentals of electromagnetism. To make it easier for you to see, I will show you an illustration.
When magnetic field lines pass through a surface, flux will be produced since there is presence of magnetic field intensity. Flux represents the number of field lines. When the surface is rotated about the field line, it does not affect flux at all. However, if the size of the surface changes, flux will change too. They are directly proportional to each other. For example, if the surface increases, flux will increase too, and vice versa. For magnetic intensity H is H equal to U divided by L, where U is the magnetomotive force acting on the surface in ampere or ampere turn. L is length of surface in meter. The unit for H is ampere per meter. The equation for resulting magnetic flux density is B equal to flux over A, where flux is in unit of Weber and A is the cross-sectional area of the surface in square meter.
In this part, I will show you the most important discovery in electromagnetism made by Faraday. After performing many experiments, Faraday finally reached his final conclusion, which shows the fundamental relationship between voltage and flux in a circuit. This is called Faraday's law in electromagnetism induction. He performed his experiment by moving a magnetic bar in and out of the induction coils. Here he observed two things. First, when the flux linking a loop or turn varies with the time, there will be an induced voltage between the terminals. Second, the value of the induced voltage is directly proportional to the rate of change of flux. In other words, if induced voltage is increased, rate of change of flux will increase too, and vice versa. From these relationships, an equation showing the relationship is E equal to N delta flux by delta T, where E is the induced voltage, N is the number of turns in the coil. Delta flux by delta T is the change of flux over change of time in Weber per second. To make it easier to calculate the induced voltage, it is normally referred to conductors rather than the coil. Therefore, the value of induced voltage across a conductor terminal is E equal to BLV, where E is the induced voltage, B is flux density, L is the length of conductor in magnetic field, and V is the relative speed of conductor.
Okay, I'm going to tell you about the fundamental idea that lies behind the operation of motor generators and many other electrical instruments. It is the Lorentz force or electromagnetic force. It is a current carrying conductor in a magnetic field. Here I'm going to show you a clip showing an experiment to allow you to visualize it.
The circuit here consists of two magnetic poles, North Pole and South Pole. He separates them with plastic so that the moving of wire can be observed easily. The moving of wire shows the direction of force. According to the right-hand rule, we can tell the direction of field, force, and current. However, there will be force if the conductor is perpendicular to the field lines. When the conductor is parallel with the field lines, force will be equal to 0. What does the force really look like, or what is the shape of the resulting force? In order to answer this question, we have to look at the lines of the force produced by the conductor and magnetic. Above the conductor, flux density of conductor and magnetic acts in the same direction and in the opposite direction below the conductor. Therefore, the number of lines above the conductor is greater than those below the conductor.
When talking about the magnetic force and magnetic material, term residual, flux density, and cohesive force are to be considered. As we increase permeability, there will be electricity feed into the metal bar, and once we pull the bar out of the system, the bar will be magnetized, but just temporarily. The leftover magnetic is called the residual flux. Starting with current equals to 0, and we will slowly increase the input current. Once current is increased, flux density B and magnetic field intensity H are also increased. Here is the test of the system. When B reaches its maximum value, H will too reach its maximum value. However, if we reduce current, B will move in a new path as shown here. However, H will remain constant. This phenomenon is called hysteresis. When H is equal to 0, B will remain constant, which is called the residual flux density or residual induction. The total area of this curve represents the power loss and power gained. In order to reduce the residual flux, we need to reserve the current in the coil to increase H in the opposite direction. The magnetic field intensity used to reduce flux to 0 is called coercive force. Here is cohesive force. As the magnetic material absorbs energy, there will energy loss in form of heat in every cycle, and I will show you after this. The graph shows heat release or the hysteresis loop in one cycle. Heat release is in joule per kilogram. This graph is called hysteresis loop. Hysteresis loss appears when a piece of iron rotates in a constant magnetic field. In order to get a machine such as transformers to work at good efficiency, we need to reduce the hysteresis loss. By doing this, we need to choose the material with a narrow hysteresis loop.
What is the cause of power loss in metal? One of the causes is eddy current. Eddy current is an unwanted current that flows in the core of metal circularly. It is produced from flux.
So how can the eddy current be produced? Imagine if you take a solenoid, connect it with an iron core and connect the solenoid with iron core with an AC source, then try to hold a metallic disc above the system. The disc will fly off into the air. This situation happens because there is a change in magnetic flux which increases the induced current of the disc. This illustration shows that when a conductor is in a changing magnetic field, there will be induced current in the core of the conductor. This current will flow in small loops, and they are the eddy current. In order to reduce eddy current, we have to split the core into sections. The more we split the core, the more eddy current will be reduced. Here I will show you the proof using equations. From R equal to rho, I divided by A. If we split the coil in half, it will be R equal to rho I divided by A over 2. And at last it will result into R for electric. And from R equal to I over mu A. If we split the coil in half, it will be R equal to I over mu A over 2. And it will become 2R for magnetic as well. From these two proofs, we can see that the new resistance is the twice of the old resistance. With low resistance of the plate, there will be large eddy current. Therefore, we want to increase the resistivity in order to decrease eddy current. When eddy current is reduced, we also reduce the loss of power. Power loss here is in form of heat.